Okay, hi everyone. My name is Alana Pindar. Thank you for joining, particularly those online and those that are in person at SMU. We are so delighted to have you for our lecture series for the month. I'd like to start off by acknowledging that we are gathered on ancestral and unceded territory of the Mi'kmaq people. This land is known as Mi'kma'ki. It is covered by the treaties of peace and friendship, and it was signed by the Mi'kmaq with the British Crown, which recognize Mi'kmaq title and our ongoing agreements today. We are grateful to be living and working on this land, and we are committed to working towards reconciliation. And on that note, I am delighted to introduce you to you this evening, Dr. Svenja Huntemann, who is joining us for our December series. I would like to give you a little bit of background about our speaker this evening. She completed her bachelor's degree from UNB in 2012 and continued on to do her master's and her PhD at Dalhousie, where while she was at Dalhousie, she was responsible for the Nova Scotia Math Circles program for several years. She continued on to do an NSERC funded postdoctoral fellow at Carleton University and is now at Mount St. Vincent as a professor. She was the recipient of Mount St. Vincent's Early Career Research Excellence Award, and we are delighted to have her speak to us this evening. I know her talk is going to be extremely interesting, and I, for one, cannot wait to hear it. So without further ado, I would like to give a warm welcome to our speaker.
Great. Thank you, everyone. So my title is Combinatorial Games. Would you like some math with your game? So we're going to start, I think in my abstract I said we're mostly going to focus on two separate games, and I'm going to introduce you guys to the main questions when we're talking about the sorts of games that I'll talk about, and also the sorts of questions that I look at in particular with my research groups. So the first game that we're looking at is domineering. Looks very pink and blue. This is supposed to be red and blue, but we'll go with pink and blue for tonight. So the game domineering, how it's played is we have two players. We play on a grid. So in this case, down here I put a 6x6 grid. Quite often you play on a chessboard, so an 8x8 grid. So that would be kind of a very common one. And then the two players, one player is going to put a domino down horizontally, and the other is going to put dominoes down vertically. And so in this case, I had the horizontal player going first. It doesn't actually matter who goes first for a square board like this. And then maybe the other player puts one down here, and maybe the horizontal player puts one down there again, and vertical puts one maybe down there. And we're going to keep going like this. And now in this case, they've each had 7 turns. It would be, sorry, red had 8 turns, the horizontal player. It would be the vertical player's turn. They can't put a domino down anywhere anymore without overlapping, which means they've lost. So our kind of goal here is to be the last person to put a domino down, and then you've won the game. Seems pretty simple, the rules. Turns out this game is actually very difficult. So this was introduced by Göran Andersson in the 1970s and then popularized by Martin Gardner. Martin Gardner wrote a column, a newspaper column for a long time where he would look at interesting recreational math things. And one of his columns was about this game. It was called cross-cram at the time. We now call it domineering for the dominoes that we're putting down. All right, so this is going to be one game. Anyone have questions about domineering right now? Immediately? Okay, the other game that we're going to look at is a game called Snort. Before I can tell you about Snort, though, we're going to have to quickly look at what is called a graph. So we're not talking about a graph here like you guys might know, like a pie chart or a graph of a function or something like that. Instead, what we're going to look at is we have a collection of dots, which we call vertices, And then between them, we're going to put some lines, and we'll call those the edges of the graph. Now, these are often used to represent relationships. So the vertices, the dots can represent objects, or people, or places, or whatever you want. And the edges would be relationships. So if it's people, it could be people who are friends with each other. We're going to put a line between them. Or if it is cities, we could put a line between them if there's a highway from one city to another one. So that's kind of the common one. I have a few examples. So social networks is a very common one. Road maps, like I was just saying, if there's a road between two cities, we can do that. Electrical networks really are some too. Molecules, right? If you have bonds between atoms. Genealogy trees and evolution trees are also examples of graphs. Here's an example for a social network. This one is taken from Facebook directly. They had an intern probably about 15 years ago, almost now, map all of the users on Facebook and who they're friends with. Now, this is, of course, obviously quite outdated, but it's, so the white dots are the users, the blue lines are if they are friends with each other. And of course, you can very noticeably see that Russia is missing. So there's some interesting stuff that we can look at for these. Here's an example of an evolutionary tree. So that would be kind of a graph example. And here's an example of IP traffic. So we have IP addresses, and then we put lines in between if they're communicating with each other. So there's all kinds of interesting things, interesting stuff that you can represent with graphs. Now, my talk isn't actually about graphs, though. We're going to look at games, but I wanted to quickly tell you about graphs. And so the game Snort, we are going to play on a graph, which could be a grid, but it could be all kinds of weird stuff happening as well. So here's, in this case, I gave you guys a 3x3 grid where we kind of have horizontal and vertical adjacency. We again have two players play on a graph. And this time we have that the two players are going to color the vertices, which is why I left big space inside so we can color them. And we call that claiming that vertex. So one is going to color in blue, and the other one is going to color in red. And we have some restrictions, though. We're not just going to color the vertices until we're full and we're done. We're going to have some restrictions on what we can do. So once the blue player has colored this vertex blue, the rule for Snort is that now the red player cannot play in these two. So you cannot play if there's a line in between to the opposite color. So in our case, red might instead go down here. And then now this vertex, neither player can go anymore because it would be adjacent to both blue and red. Instead, maybe blue says, okay, I'm going to play right here. Red says, oh, I'll play here. Now it's blue's turn, and blue says, oh no, I can't go anywhere anymore. Every one of the vertices we have left has a line to a red vertex, right? So, and we have that same rule again that we had for domineering. If you can't make a move on your turn, you've lost the game. And so this is kind of what we're assuming here. Okay, questions about Snort? I told you guys about domineering who introduced this. I should tell you guys why it's called Snort. It's called Snort because Simon Norton introduced it. And so it was just an abbreviation of his name. Also, sometime in the 1970s that was introduced. If it's played on grids, it's also sometimes known as cats and dogs. The two players, one player puts down cats, one player puts down dogs. Cats and dogs can't be near each other, so we have to have space between them. And one really interesting thing is in Portugal, they have for high schools and I think even elementary schools, they have these game championships. And so cats and dogs is actually one of the championship games that they play there. So there's thousands of kids that play that game. All right, so that's Snort. Now, what these games have in common is they're both combinatorial games. So combinatorial games, for our purposes, are going to be two-player, perfect information, no chance games. Perfect information means there's nothing that's hidden. So for example, if you're thinking about the game Battleship, well, I don't see where my opponent has their ships. Perfect information is I know everything about the board. So Battleship is not allowed because I don't have full information about the game state. No chance, meaning we're not rolling dice, we're not drawing cards, nothing like that. In theory, this means if we had enough time and enough computational power, we should be able to figure out every single possible line of play and be able to compute everything. Now, in practice, for a lot of games, that's just not possible because there's too many possibilities for what we can look at. I have an example bar there. So with the description that we had, I already told you Snort and Domineering are combinatorial games. So my first question to you guys is, what other games can you think of that would be combinatorial games?
Checkers, checkers.
Chess? Checkers? Other games?
Boxing.
So boxing would not, because I think there's too many variables involved. Just because I think there's some probabilities and you don't actually know what your optimal move for your opponent is. Not an interesting one. I don't think I've ever had that as an answer. You might have heard of the game Go. So that one, I know a few years ago it was huge in the news because for the first time ever, a computer player had beaten the world champion in Go. And that was a huge deal because chess, I mean, the computer players have been able to beat the world champions for quite some time, but Go is like several orders of magnitude more complex than chess. And so that was a huge deal when that happened. Which, by the way, at the University of Calgary, a researcher in computer science called Martin Mueller, several of his PhD students worked on the program that beat the world champion. So it's kind of an interesting Canadian fun fact. All right, so then you might have also heard of the game Hex, maybe. Halifax actually has a Hex club, which Peter Selinger right there started. And Peter does some research on Hex as well with his students too. So that is kind of one that happens. And the other one that you might possibly have heard of is a game called NIM. Like a lot of people kind of learn about that if they learn about binary numbers. I know I've done it with a lot of kids in school. You play it on piles of tokens, you take tokens and take turns. Whoever takes the last token wins. So that's combinatorial games. Notice I put even my checkers in red and blue. The reason why is in combinatorial game theory, we often think as red and blue as the two players. White and black is kind of the alternative, but usually red and blue is what we use. And the blue player we call left, and the red player we call right. There's a reason for it, because in notation we're going to put left on the left, right on the right. But the other thing that's kind of interesting is we use female pronouns for left and male pronouns for right. And there's another interesting Canadian tidbit why that is. So one of the founding fathers of the area of combinatorial game theory was Richard Guy, who was a professor at the University of Calgary. He actually was one of the founding professors there, so he was one of the first few hires. And so Richard Guy, his wife was Louise. So Richard right is female and Louise left is female. Richard Guy he passed at the start of COVID. I think he turned 104 and he was still doing research until shortly before his death, quite actively supervising people. All right, so that's combinatorial games. So like I said, kind of in theory, we should be able to analyze every single possible situation. In practice, that's just not possible. Like if we were to analyze every single possibility in Go, if we did one per second, by the end of the universe, we still wouldn't be done. So that's just not feasible. So we're going to use some other tools instead of doing a complete analysis for these games. So our question is, who wins the game and by how much. This is what we're going to answer. Well, try to answer. We're not going to be able to for everything. So a little bit of a short history. I gave you guys already a little bit. So the game NIM was solved in 1902 by Booten. That was the very first paper in combinatorial game theory. So that's kind of like in terms of if you're thinking in the length of time, it's a relatively new field. Then in the 1930s, this great Grundy theory was introduced, which I'm not going to cover, but that was kind of the next step up. And so they were basically showing that a lot of games reduce down to NIM, but that doesn't happen for the games that we're looking at, Synod and Domineering. You can't do that reduction to NIM. And then in the 1970s, Alvin Berlekamp, Conway, John Conway, thank you. I can't think of his first name. And Richard Guy, they kind of discovered that there is a lot of algebraic structure underlying these games. And they published a few books on it. I forgot it, I had it in my, and they have the winning ways in my thing I was going to show people. So this is the second edition of one of the books that they published, and I'm going to try and show online too. But one of the really cool things that I think about this book is that all of the diagrams in this book were hand drawn by Richard Guy. I don't know if you guys can see. I'll hand it around. I'll show you the people online quickly. But if people want to leaf through, like he hand drew all of the diagrams in this book, which is pretty awesome. John Conway also, if you've heard of Conway's Game of Life, that is that same Conway. If you haven't, an interesting one to look into. All right, so that is kind of, this really started modern combinatorial game theory. And since then, the area has massively exploded. In terms of connections, like within mathematics, we're kind of this little field. I would say worldwide, there's probably less than 100 researchers in combinatorial game theory. But there is all kinds of connections to other areas. So we're kind of pulling other people in by doing stuff with them. One of the first ones is an area called combinatorics, and that is kind of the tightest connection, which is why the area is called combinatorial game theory. But then also number theory. If you guys are coming to the talk in May, Karen McLellan, my colleague from the Mount, is going to speak then. She works in number theory, so you'll learn a little bit about number theory then. Other areas called set theory, abstract algebra, not kind of the algebra that you guys learned in high school, but thinking very abstractly. But also on the computer science side. So it's, even though most of the area falls within mathematics, it's kind of the sliding scale going into computer science as well. And so one of the things is computational complexity. That is basically asking the question of how hard is it to calculate something. I'm not going to talk about this today, but there is a huge amount of work on showing how difficult it is to compute stuff about games. And then the other one, of course, is artificial intelligence and machine learning. There's a lot of stuff there, and I'll talk a little bit about how we bring machine learning into our research as well. All right. So one of the first few tools that we use is the so-called disjunctive sum. So here's a small domineering board. We've already made a few moves. And so what happens a lot in domineering is after you've made a few moves, the board breaks down into these smaller regions. And so in this case, we have kind of the 2x1 up there. We have this little square with an extra shape, almost T-shape in a single square. And when we make a move in one of these regions, that can't ever affect the other region because they're completely disconnected. And so when we have this, we write this as a sum. So we basically say we're taking this, adding this other region, adding the third region, and adding the fourth region. We call this the disjunctive sum of two games. And so what we need to do in this case is we need to say, okay, if it is my turn, I need to pick which one of my regions I make my move in and make my move there. And then it is my opponent's turn. They decide which one of the regions they want to make them move in, which could be the same one that you just moved in or a different one, and so on. And so this is disjunctive sum. We say on your turn, you pick which one you make your move in, make your move there. One thing to point out is when we are working with disjunctive sum, so in particular with the square up there, suppose it is the horizontal player's turn or right's turn. They make a move, can't really point out, I'll use the mouse so that people online can see too. So if right moves here in this square, then maybe, well, now left, the vertical player can only move here. Right might go again and say, okay, I'm going to move here. So within a component, you might not have that the players alternate anymore. And that's going to become relevant later on. So within a component, we don't necessarily have alternate. Okay, so this is disjunctive sum and domineering. Happens in snort as well. It's a little bit more complicated there though. So what we do in snort instead is we basically, when we color a vertex, we can think of removing that vertex instead. But we somehow need to represent that the other player can't go in the two vertices next to it anymore, or many vertices next to it. So here I just have kind of a string of vertices. So how we do this is we say, for the ones next to it, we're going to tint them blue. And tinted blue means only the blue player can go there. If it was a red vertex, we're going to tint red to represent that only the red player can go there. And so now we now have these disjoint regions, and I didn't put a plus in between, but this is still a sum in between. And then if red goes next and maybe moves in the bottom one here, now we would have, well, only blue can go here, but then after red goes, only red can go here. Those kind of contradict each other, so we're also going to remove that vertex. So if you already have one that is tinted, then you remove that entirely. So after the two moves, we would have one tinted red and one tinted blue that are remaining. And then blue would go, red would go, game is over. But this is how we can get disjunctive sum and snort as well. So for both of these games, this happens for a lot of games quite naturally that we're looking at a disjunctive sum. Okay. I know I've thrown a lot of stuff at you guys. Any questions right now?
Just with respect to snort, you mentioned the normal board people play on the domineering is 8x8. Is it usually 3x3 for snort?
No, snort there's no real starting position. I think in cats and dogs you usually play on like a 5x5, but you doesn't even need to be a grid for snort. It can be like some weird stuff. I'm going to show you guys some other graphs later on as well. Good question though. All right. So let's go into how we use this. So first research question that we are asking about is, which player wins the game? So that's our main question that we ask in combinatorial game theory, the main thing that we want to answer. And so how we what we use here is so-called outcome classes. So outcome classes is every one of my regions I'm going to assign into an outcome class. We have the first player wins, no matter if that's our left player or right player. The second player wins, so the second player to go, which would have been the one who just made a move. We call that P for previous, and I should have said first is N for next. And then we can have that the left player, which for domineering was the vertical player, wins no matter who goes first, or the right player wins no matter who goes first, which was horizontal player for domineering. Okay, so the issue is if I have a big game, it can be really difficult to figure out which one of these we fall into. So our goal is to look at each one of the regions separately, analyze those. They're much smaller, much easier to deal with. And then kind of use this information that we have for each region, compile that together into something for the overall game. So that's kind of what we want to do to simplify our computation. Now, let's first look at a few of these outcomes in domineering so that everybody's okay with these. If I have a 2x1 like this one, and I'll kind of remind everybody again, left is horizontal, right is, left is vertical, right is horizontal. I always mix the two words up. So left goes vertical, right goes horizontal. Who wins if I have just this little region? Left. Because if left goes first, still put our domino down and wins. Right goes first, can't put one down and loses. So that one is a left win. If I do a 90-degree rotation, that's going to be a right win. So same thing. What about if I have a 1x1 square? The previous player, because it's basically saying, well, whoever goes first is going to lose, so the other person wins. So that's kind of a weird situation that we're saying. So whoever goes first loses, which means the second player or the previous player wins. We're going to put the single square into P. What about this little L shape?
Yeah, that's right. First.
Who's first in this one? So that's an N or next win. What about the 2x2 square? Next also, I have one more for you guys, a bigger L shape.
Depends if horizontal goes first, what they choose to do.
Yeah. So I'll use my mouse again so all people online can see. So if vertical goes first, vertical has to go here, doesn't have a choice. And then horizontal can go. Vertical can't do anything anymore and loses. If horizontal goes first, this move would be a bad move for them to make. So they're never going to make that move. So they're going to go here instead. And then vertical can't go and loses. So in this case, the horizontal player wins no matter what. And we called that a right win. So for this L shape, that's a right win. If I rotate it, it becomes a vertical win or left win. Oh, right, I forgot I have the Z shape too. What about this one?
If horizontals first, they win. If verticals first, they win.
Yeah, so whoever goes first wins.
Yeah.
So this one is also a next. Okay, so people feeling pretty okay with these ones? Now, so what we said is we want to be able to use the analysis of the smaller components to be able to learn something about the bigger game. So let's look at what happens if I'm adding two of these together. So here we have a left win plus a left win, or a vertical win and a vertical win. So if vertical goes first, they win. If horizontal goes first, they lose. Well, this one is a vertical win. And it turns out whenever you have left plus left, you get a left back out. Fortunately, it's not always that nice. So here's two situations where we have a left win plus a next win. So we saw that both the little L and the square is a left. We're looking at the top one. I'll have you guys think about it for a moment again. Who wins in the top one? Okay, so if right goes first, the horizontal player, they can only go here. Left goes and wins. If left goes first, the vertical player, where are they going to go? Are they going to go here? No, that's the bad move. So they're going to go here and also win. So the top one is a left win. The bottom one, what are the players going to do for their first move?
Similar to what you just described.
Yeah, so left, it's a bad move to go here, so left is going to go in the square. What is right going to do? Well, they have to go in the square. Then left has to go here. They have no other option. And right can go again in the square in the other half of the square. So this one is going to be whoever goes first wins. So on the top, we had a left plus an x that gave me a left. And on the bottom, we had a left plus an x that gave me a next. Well, that's a bit of a problem because we should only have one possible answer. So here's kind of our full list. I'm not going to make you guess do all of the possible combinations. But we have left plus left is always in left. Left plus a next could be left or next, like we just saw. Left plus a right could be anything. We can actually have all four. Left plus previous is left, right plus previous. So we have a bunch of question marks or ors in there. We have a bunch of situations where we don't know just based on outcome class who wins. So we don't get unique answers, which is a bit of a problem. We would like to have unique answers. So what we're going to introduce is so-called game values. I'll go back again to our previous example. Does anyone have an idea why in the bottom one, whoever went first wins, while in the top one, they didn't? So in the bottom one, whoever went first, by moving in the square, reserved themselves another move. Why with the little L shape, if you went there was no further moves in there. So we're going to have to represent this, like we have to somehow distinguish this, that in the little square, you actually gained a move, a guaranteed move by moving first. While in the little L shape, you didn't. So this is where we bring in game values. So game values is kind of, the question is, how much of an advantage do you have if you're going, like if you're the winning player? Like how many guaranteed moves do you have? So we're going to say that two games are equal to each other if I can swap them out in a disjunctive sum without changing who wins. So in a domineering, if I have a single square or I have nothing, that's really the same thing. Because in a single square, you can't move. The other one that is kind of the same, I don't know if people online can see this, but I also don't know if it's bright enough for you guys. No? All right. In domineering, if you have like a 1/2 or a 1/3, both of those are one move for left. A 1/3, yes, you could go at the top or at the bottom, but you can still only make one move in a row in it. So those two games are really the same thing for our purposes. Left makes a move and it's done. Right can't make any moves. So we're going to call these equal to each other. And the value, for all intents and purposes, is the simplest game that is equal to it. So we have some reduction, which I'm not going to tell you guys about because they get a bit formal. But we have some ways to find this simplest game equal to it. Okay, so what we're going to do is we're going to say that a game, and this is where that nomenclature of left and right comes in. We're going to use curly brackets, and everything left can do, we're going to put on the left side of a vertical bar, and everything right can do, we can put on the other side, and then put a curly bracket again to close it. And so this is the notation that we use for a game. The negative is, and this actually works, I can do G plus the negative, and I get 0, which is nice. We're going to swap it. If you don't worry about following the notation, but really what the negative is swapping left and right's roles. For domineering, that means we're swapping who's vertical and who's horizontal, which means we're rotating by 90 degrees, which we've done for a few of the little positions we've already looked at, right? We said if I had a 1/2 in this direction, left was winning. If I have a 1/2 in this direction, right was winning. For snort, you're just going to swap colors. It's literally all you're going to do is everything that was blue before becomes red, everything that was red becomes blue, and we're done with that. Okay. I don't know if people online could see the board if I turn on partial lights. I wanted to give some examples. I'll do a few examples and then
Raise your eyes, I'm not sure.
okay. Is this okay for people to see the board? All right. So the first game is what we call the zero game. So this is the one where neither player can make any moves. This was the one in domineering where we had a little 1x1 square. Because we're basically going to say, while left goes first, they can't do anything, so we're not going to put anything on the left side. We're going to put our bar. Right goes next, can't do anything, so we're not going to put anything on their side. And so this is our game that we call zero. Neither player has any moves. Now, I didn't mention it earlier when we had it on the slide, but one of the things we do is we say left is going to be positive values and right is going to be negative values. So let's think about this 1x2 that we have. The 1x2, if left goes, after left goes, it's empty, which is that zero game. So left moves, makes a move, goes to the empty game. I'll kind of draw it once with the domino put on top. There we go. Right, again, has nothing they can do. So they're going to have empty. So we call this one, where left goes to zero. Right has nothing. This is one move for left. Left can make one move. So we're going to call this positive one. It's one move. Now a 1x3, I'm not going to put it up, but a 1x3 was left can still only make one move. We're going to have that single square left at the end. This one though, well, left could go here or here or here. Go up in the middle is a stupid move to make, so she's not going to make that move. Instead, she's going to go on the top, and then we're basically going to think of as deleting this, and we're left over with this one. That's kind of what's remaining. So this is, we said this one was one move for left. Right, still has nothing. And in total, this is two moves for left in a row. So we're going to call that one 2. And we can keep doing this. So we're going to get 3, 4, 5, 6, and so on. You're trying to see if the camera, is that helping?
Yeah.
Okay. So these are what we call the positive moves. And then I said for right, we're going to call these negatives. So we're going to do the same thing, and we're going to say that this would be -1. And then if I kind of keep going, we get -2, -3, and so on. So this is kind of the easy ones where I say, okay, we definitely have a straightforward, we can count how many moves each player has. So we're going to get 1, 2, 3, -1, -2, -3, and we get all of the integers this way. So we can keep going and going and going. Now, not every domineering position is going to be that way, though. One of the first ones that we had was the little L shape. The little L shape, well, whoever goes first wins. And in particular, they're going to go to, there's nothing left to do afterwards. And we call the nothing left to do afterwards 0. So we're going to call this one left goes to 0, right goes to 0. And this one is weird because it's not 0, it's not positive, it's not negative. So that doesn't happen a lot in a lot of the things that you guys probably do. You can almost think of this as like this vague cloud that lives around 0 but isn't actually equal to 0. This this game value happens so much that we give it a shorthand, and we're going to call this star. So it doesn't get a number. It's not positive, it's not negative, it's not zero. It gets a symbol, a different one. And then I'll skip showing it for domineering, but in a game like NIM, we'll also get star 2 and continue on star n. They're called nimbers, come from NIM. We get some weird stuff there. Next one I'm going to ask you guys about, because we said this one was the important one when we're doing the left plus next, is here we didn't gain anything. Here we're going to gain, right? So if left goes first, what is she going to go to? What is going to be remaining after left made her move?
Usually just a vertical 2.
Yeah, which we called that one 1, right? So after left moves, we have a 1 remaining. After right moves, we're going to have a -1 remaining. So this is again something that's neither positive nor negative nor 0. It's another weird one. We call this one just plus or minus 1. Of course, whoever goes first is going to gain a move. In these other ones, it was basically, okay, you're losing moves as you're moving. But in this one, you're gaining a move as you go first. So plus or minus 1. And we have all kinds of other weird stuff that happens for game values. We do have fractions as well. The longer L shape is not quite, it is an advantage to either left or right. So it's going to be positive or negative, but it's not a full move advantage. And it turns out if you kind of think about it, half of the time the winning player gains a move. So we call that a half and negative a half. So we kind of get fractions this way as well. Okay, so this was my crash course of game values. I'm going to go a little bit faster. So one of the research questions that I look at is if you're looking at games similar to Snort and Domineering, where you're only putting pieces down on the board and you're not moving them around, it seems like they should be simple games, but they're actually pretty complex to analyze. But we do have some nice tools in mathematics you can use. And we call these games SP games. So we want to kind of figure out, if you tell me a game, can I figure out all of the possible values that we can have? So in Domineering, for example, we don't actually think we get all of the values. Some of the values in NIM, they don't appear in Domineering. So in general, very little is actually known for what is possible. We do have an extra game called Call. Call is like Snort, but this time you can't go next to your own color, but you can go next to your opponent. That one, it turns out you can only get numbers, so like the integers and the fractions, or that plus this value that we had that we called star. That's the only thing that can happen there. For Snort, our computational evidence also indicates that we can only get certain things. And this is something I'm working on with a collaborator of mine right now, Neil Mackay at UNB. And we're trying to show that this is indeed the case. We can only get these particular values. And the reason why we want to do this is basically to say, it's like, okay, I know I can only get these values, so maybe I can get my computations faster because I know I don't need to consider certain things. Domineering, there's been over a dozen papers that have studied the values of domineering. We still don't know. There's a lot of like guesses that certain things can't happen, but there's been no proofs yet showing that certain things can't happen. So there's a lot of work that can be done in that direction too. There's something called universal games. Universal games are games that actually do have all of the possible values happening. It's this massive universe and all of them happen. In the last, I would say 10 years-ish, there's been a few games that have been found that are universal. But none of these are these placement games where I'm putting just tokens down. All of them had some sort of moving thing to it. So our question is, can we find one that is universal? So the reason why we want to do this is if the answer is yes, every possible combinatorial game is going to be equal to an SP game. I don't think this is actually going to be the case, but if that was the case, we could use tools for placement games. No, we can again reduce, like simplify the calculations a little bit. So this is another question that I'm looking at. Quickly, one other question is, so all of the games I told you so far were, if you couldn't make a move on your turn, you've lost. We also have so-called misère play, where if you can't make a move on your turn, you win, but pretty much everything falls apart. It's weird, even though we're just making the small change, like a lot of the, like we can't even subtract games anymore, which like our basic operation falls apart. That's why a lot of people joke that misère play is miserable. Stuff just doesn't work well. So our question then is like, well, if we change who wins, can we figure out what happens for these placement games? And again, regional, like Rebecca Milley at Memorial, she does a lot of work in this area, and her student have looked at things. I do some stuff at her too, so we've started looking at what happens in Snort, and then this related game Hull, if I'm kind of changing who wins and stuff is weird, to say the least. You even have that 1 is no longer bigger than 0. It's like some really weird stuff happening. Okay, so the last thing that I'll tell you very quickly about is a tool called temperature. So value was how much do I, how much of an advantage do I have? Temperature says, how urgent is it for me to make the first move in a component? So that's kind of measuring what temperature is. Boiling point is, well, if you give me all of domineering, what is the biggest temperature I can get? All of snort, what's the biggest temperature I can get? Problem is, it's actually really hard to calculate what temperature is for a position. So instead, we try to find approximations or upper bounds. The reason why upper bounds are particularly interesting is a lot of computer players, computer programs that play games, they actually use temperature to decide which move to make. And so if you find, okay, in this game, the highest temperature you can get is 100, if the computer player finds one that has temperature 99, it might say, oh, well, this is good enough. I'm going to make this move. But if you don't know that the biggest one is 100, it might say, oh, maybe I should keep going and try and find something better. Richard Narkowski right here from Dell and Carlos Santos from Portugal, we actually proved the very first upper bound that works for all games. Still difficult to calculate for a lot of stuff, but particularly for placement games, it's a nice one that kind of works well. So question is, what is the boiling point of a placement game? For call, it turns out it's 0, because when you're moving, you don't really ever want to move. You're kind of losing options because you can't go next to yourself. So that one is a bad one. For snort, I'm claiming we have unbounded temperature. So here's a position that's not a grid. Which one is the good move that we should be making? In the middle, right? We're going to move in the middle. And when we move the vertex, all of them are now reserved for me. So I've gained 4 moves with this. And we can do this, we can add more of these so-called leaves to the center. So I could add 10 to the outside. I'm going to gain 10 moves. I can add 100. I'm going to gain 100 moves, and so on. So I can add as many as I want, so my temperature could be as high as I want. Now, this was a big mistake in my PhD thesis. I wrote down saying, oh, I think in snort, the biggest you can ever get is the biggest degree, where degree is how many edges are connected to a vertex. Because we had in this position, however many were connected to that center was what I gained. A few years ago, we found one that actually had it just a little bit higher. The temperature was just a tiny bit bigger than that. And then I stuck one of my students on it who is a really good programmer, and he used machine learning to find positions that got higher and higher and higher temperature compared to the degree. And we generalize this to these caterpillars, and we've shown that they have temperature to n+1. The degree is only n+2, so kind of the more vertices I'm adding to it, the bigger of a difference I'm going to get. So we're kind of getting this bigger and bigger and bigger difference for this one. So that is, we're still doing more on this. There's some related questions. It's kind of a question of, can we look at other graphs? Can we get some other sort of restrictions for snort and so on? The last question is the boiling point of domineering 2? That number seems to come kind of out of nowhere, but this has been conjectured since the 1970s to be the case. People are now calling it Berlecamp's conjecture, although it's not certain whether Berlecamp actually made this conjecture or not. He just asked, what are the possible temperatures in domineering? So it's kind of, this is what we call Berlecamp's conjecture. But this is like the longest standing open question in combinatorial game theory, is we still don't know whether this is true or not. And again, there's been probably a good dozen papers on this, and people have been finding more and more stuff, but nobody's been able to show yet whether this is the case or not. And with that same student, Tom, who's at MUN now, he was somewhere else before, we again used some computer search, both complete search and also machine learning, and we found thousands and thousands and thousands of positions that have temperature 2, think bigger. But one of the things that we found is that all of them have something called a hook. And so our question that we're interested in is that hook actually a necessity to have high temperature? And then everything that actually had temperature 2 contains something called the Drummond-Colt position. That is the very first position that was found to have temperature 2. So the other question that we have is, domineering is played on a grid. Is it because of the grid that the temperature is at most 2? For snort, we said we can play on all kinds of weird stuff. And so this is work I'm doing with Neil Mackay from UNB again, and Craig Tennenhouse in Maine. And we looked at a generalization of domineering where we get rid of the grid structure, and we've shown that that one doesn't have a bounded temperature. So it seems that the grid has something to do with the temperature stuff. Okay, thank you, everyone. Do people have questions?
Yes, let's see if anyone online.
Yes.
One just to start off.
Yeah.
With snort with the grid, the way I'm picturing, I feel like it doesn't necessarily get to the core of what we know about it. But my mind and that last thing you just mentioned was along the lines of, if you have essentially like 2D grids that are stacked and only accessible for certain connective points.
Yes.
Does that somehow potentially impact that? Does the grid equal y2 comes up?
Okay, for domineering, I mean, there's definitely some conjecture that it might be somehow that we can somehow put some boundary around it, and within that boundary, you are guaranteed to gain 2 moves, but not more than that. But we haven't been able to show it yet. So we definitely think it has something to do with that structure, but it's not clear.
No questions online.
Okay.
Another follow-up then. So with domineering, there's the vertical and horizontal. Is there an equivalent in 3D space where there's the in and out of plane position as well?
Yes. A third player. 3 players becomes interesting because you're no longer just looking at like a theoretical approach. You now need to say, okay, if it's my turn, I know I'm going to lose, but my move determines if player A or player B wins. So now you need to make a decision which player you're going to have win. And so then now we're getting like all of this social stuff coming in. But three-player games is one of the things people are looking at if we're kind of making certain assumptions over who wins in certain situations. You can start to analyze them, but they become a bit messy.
Beyond the scope.
Yeah.
Questions online so far?
Okay.
They're good.
Questions online. That's a question.
Of course.
When so you have this result with canvas and very domineering on basically or something by whatever field, whatever.
Yeah.
You had unlimited temperature, wasn't it? So I mean, if it has something to do with the grid, one wonders what it might have to do with the grid. For example, is it that the grid is planar?
Yeah, and so
Like
one.
you don't have crossings, or is that like the reason, or is it
So
because of degree, for example?
it's not clear yet, because one of the questions we still have is the position we found. We now have the number of reds and blues out of a vertex are kind of keep increasing as well. And so a question we have is if we kind of keep that reduced, but don't get rid of the planarity, is do we still have that temperature bound or not? So for now, we've only shown that it's unbounded in general, but now it's kind of a question of if we kind of go deeper in, if we're looking at certain structures, is it still unbounded or not?
It becomes more and more similar to a grid.
Exactly.
What point does it become?
Exactly. So that's a huge question, but that's kind of one way that we're tackling this domineering problem. Okay.
Thank you so much.
Excellent.
Thank you.
Yeah.
Anybody'd like to join the NSIS tonight, we'll have a copy of one of our old volumes. Have a look at the ones up there.
Yeah, if your student is only $10, your regular person, you pay $30. 40, sorry, 40. But we also encourage people to give memberships. Now this is the month, where we want more young people involved in the organization. So if you think that there's someone, young person, that all will cost you will be $10. Or 30, give it to a friend or somebody.
And for those who are students or working with students, we also have a writing competition that just recently launched, and all the details are on our website. There are cash prizes, so do share with the students here.
Oh, I see. Tom is actually online. Yeah. And Melanie Gautier was another student. Did a bunch of stuff as well. So it's nice that you're there. Yeah.
Thank you.
Thanks. Yeah, I'll let you.
Yeah. And thanks everyone online for attending this evening as well. Have a great evening.